Hello, everybody. Welcome back to Markov Processes. I just came out of an office hour where we were in the middle of a question that I said I would start class with today. So here's where I always say, how's the homework going? But I've already come in with a question. So let me get my screen shared. Okay, in problem 5 on the current homework, we've got vehicles and they're type 1, type 2, type 3 vehicles, and they each pay a certain toll. And $1, $2, or $5, and we've got some questions to answer. So this is homework 7, and problem C is worded horribly. I'm a victim of cut and paste, I claim. NFT is a Poisson process with rate 5, and that's per minute. And at this point, I usually look ahead in the problem and try to figure out, is everything going to be in minutes or another unit of time? And you want to be consistent. So there is an hour there. You have to make a decision. So I am going to stick with minutes. So 5 per minute. And great. So that is, let me move this over. That is our NFT. And then we can thin this out. So this is just the total number of arrivals by time t. And then we've got an N1 of t process, and N2 of t process, and an N3, where those are the classes 1, 2, and 3, the numbers that have arrived by time t. So these guys are paying $1, and these guys are paying $2, and these guys are paying $5. And these guys come through with probability 0.8, these guys 0.15, and these guys 0.05. And so we want, in part A, the mean and variance of the amount in dollars collected in any given hour. So it's hard to tell how much money you're bringing in unless you break it down into type 1, type 2, and type 3 vehicles. So the amount of money is going to be $1 times the number of type 1 vehicles in the first 60 minutes, since I decided to stay in minutes, plus $2 times the number of type 2 vehicles in the first 60 minutes, plus $5 times the number of type 3 vehicles in 60 minutes. An expectation is a nice linear operator, so you can run the expectation through and take those coefficients out. And for example, when you're dealing with the expected value of N1 of 60, this is a Poisson random variable. It's not even a process anymore. It's the number of arrivals in the first 60 minutes, and that's a random variable. And the parameter is going to be 5 times the 0.8. So that's thinning down to type 1 vehicles times the length of time. So this is like a lambda 1, and this is like a t. And the mean for a Poisson with a parameter, say lambda, is just the lambda. So in this case, it is the lambda 1 times t. So we get 5 times 0.8 times 60. And you can do the others similarly, and you will have the mean or expected value. So the variance may be a little harder because we haven't dealt with variances that much, but you're going to get the same expression inside a variance computation. And usually variances are difficult for sums because it's not a nice linear operator. So if you have a bunch of random variables and you're taking the variance of a sum, you get the sum of the variances plus and minus covariance terms, but those don't come into play if you have independent random variables. So if you have independent random variables, you can just sum the variances. So by independence, unlike, we didn't need that for expectation, this is the variance for 1 times N1 of 60 plus the variance of 2 times N2 of 60 plus the variance of 5 times N3 of 60. And so I'm going to stick with the first term. it might be hard to see what's going on here because there's a 1, but when you pull constants out of variances, they come out squared. So this would be 1 squared times the variance of N1 of 60. And if you have a Poisson random variable with some parameter lambda, the mean and variance are both lambda. And we already know that this is Poisson with parameter 5 times 0.8 times 60. So the variance of such a random variable is the 5 times the 0.8 times the 60. So I get 1 squared, which obviously you don't need, but I want to make sure you see it when you're dealing with the 2 and the 5, times 5 times 0.8 times 60. So let me know if that doesn't make sense. Well, I'm going to go on to part B. B is a little bit ugly. We want the probability that exactly $5 is collected in a period of 2 minutes. And the best way I can think about doing this is to consider all the ways for that to happen. So we're going to be looking at time t equals 2 here. Everything is in minutes already, so that's good. And this is going to be made up of a bunch of things. So the probability, $5 in 2 minutes, we could have 5 type 1 cars and then none of the others. So we could have the number of type 1 arrivals in 2 minutes could be 5, and the number of type 2 arrivals in 2 minutes could be 0, and the number of type 3 arrivals in 2 minutes could be 0. I'm just going to write one more term, but there's several things to consider here. We could have the number of type 1 vehicles in 2 hours be 1, and the number of type 2 vehicles in 2 hours be 2, and the number of type 3 vehicles be 0. Because if we get 2 type 2 vehicles, they're each bringing in $2. So that's a total of $4, and there's another $1. So you just have to figure out all the ways to get $5. And in each of these cases, these random variables are independent. So you get to break all of these up by independence. You'll get a probability times a probability times a probability plus just write them out, and you don't have to simplify or combine anything. Let's just look at one of these terms. Suppose you're computing the probability that n2 of 2 equals 2. I picked like the worst one for illustrating something because everything is a 2. But this has a Poisson distribution. The parameter is the original parameter, 5, times the thinned out. We're just looking at type 2, so times the 0.15 probability of getting a type 2 times the length of the time interval. And so the probability of getting a 2 there is e to the minus 5 times 0.15 times 2 times 5 times 0.15 times 2 to the 2 over 2 factorial. This one gets quite ugly. You certainly don't have to simplify it. And so C is supposed to be the probability that the waiting time until the second vehicle that pays $5 comes through is more than 10 minutes. So for C, I would let T1 and T2 be the first 2 inter-arrival times for the thinned out $5 vehicle process. So you might even want to use different notation for the $5 vehicle process. And the $5 vehicle process is a Poisson process with rate lambda 3, which is given by 5 times 0.05. And so this is the probability that T1 plus T2 is greater than 10. And I could think of 2 approaches right off the bat. One of them is to realize that this has a gamma distribution, but gamma integrals are not fun, although the parameter is only 2, which gives you some coefficients times x to the 2 minus 1. It is a smallish integration by parts. The other way to approach it to avoid integration by parts is to continue by conditioning on the value of one of these. Both of these are IID exponentials with rate lambda 3. So condition on, say, T2. And personally, I think that's easier than the integration by parts, but it's up to you. Six, we have jobs arriving according to a Poisson process with rate 2 per month. Reading ahead and seeing months in the rest of this question, I think we should stick with months as our units here. So we have lambda equals 2 per month. And so this is some sort of Poisson process. And we want the probability that it will take more than 3 months to receive an acceptable job offer. So I think the first thing we should do is ignore the ones that are not acceptable. Let's thin this out to look at so these are all the job offers that I've sketched, the acceptable offers only, right? So I'm going to grab just the acceptable ones. And so we need to figure out the probability that one is acceptable. So P is the probability any particular offer is acceptable. And that is the probability we get more than $40,000 out of this PDF. Oops. 0.12341 squared e to the blah, 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 x dx. I missed an x. There's an x in there. You could do integration by parts, or you can recognize that that's a gamma, which is not that helpful because we don't have a closed form expression for the CDF of a gamma. You can do integration by parts or do this numerically on some software. That's okay. And then we look at the acceptable offer process only. So I'll let like N1 of T be the acceptable offer process. So like N1 of T is the number of acceptable offers by time T. So there's a couple of ways to look at this. I think the most natural way, given the wording, is we're just looking at acceptable offers. So we've thinned it out and we want the probability that the first offer happens. So this is time in months. We want the probability that the first offer is greater than 3 months. So one way you can do this is you can compute the probability that the first inter-arrival time for this thinned process is greater than 3. Or you can compute the probability that the number of acceptable offers by time 3 is 0. So one of these. This is a nice easy Poisson probability. This is not bad either because we know the exponential CDF, so we know those tail probabilities for the exponential. But we have thinned the process. So we're looking at a lambda 1 equals the original lambda, which is 2, times whatever you get for P. Okay, I got to do some new stuff. So let's do some new stuff. And as usual, I can stick around a little bit at the end if you have more questions. We are talking about well, we're getting away from the Poisson process. We're trying to generalize it a little bit. And in fact, we were getting away from even a generalization of the Poisson process for a bit. We were talking about transition probabilities. So we have a new notation, and we are only talking about a time homogeneous. That's always the default. continuous time Markov chain on a discrete state space, like the Poisson process. And we are using P sub ij. Now that used to be our probability of moving from I to j in one step, but because there is no one step in continuous time, this is going to be a function of t, where that's the amount of time that goes by. So this is going to be the probability that x at some time s plus t equals j, given x at time s equals I. And this would hold for all s greater than or equal to 0. In particular, this is the probability that x at time t equals j, given x at time 0 equals I. Assuming we have the Markov property, which is a statement looking like this with a whole lot of further back history that is allowed to be dropped if you have a Markov process. So we talked last time about putting them into a matrix, a probability transition matrix. And I've always used this kind of bold P, but it's going to change in time. So now it's going to be a matrix that depends on time. And this is not going to be all of that useful to us, because we're going to need a different matrix for every period of time we want to look at. So this is not great, but today we're going to figure out a better way to describe transitions for continuous time Markov chains. However, last time we showed the Chapman-Kolmogorov equations. We can say that we can go from I to j in s plus t units of time by going to some k in the state space in the first s units of time, and then multiply independent excursion going from k to j in the remaining t units of time, or the other way around. And so this is the ijth entry of the matrix bold P s plus t. And here we are running across the ith row of bold P of s. And here we're running down the jth column of bold P sub t. So what we're really seeing here is that the matrix at time s plus t can be gotten by matrix multiplication of the matrix filled with probabilities at time s times the matrix filled with probabilities at time t. So that's the matrix version of the Chapman-Kolmogorov equations. And looking at time s plus t, we could have easily gone to some intermediate step in the first t units of time, and then the remaining stuff in the last s units of time. So while it's not obvious from this, you can easily interchange these. And therefore, you'll see that you can get the ijth entry from the matrix at time s plus t by multiplying the matrices in the other order, which is not something that you usually expect out of multiplication of matrices. They don't usually commute like that. But transition matrices are nice. So that's where we were. And let's figure out these transition probabilities. I don't want to put them in a matrix, for a Poisson process. We want to go from some I to some j in t units of time, and the Poisson process can never decrease. So the probability of going from I to j in t units of time is going to be 0 if j is less than I, because you can't go down. And the probability of going from I to j in t units of time, if j is greater than I or equal to I, this is not a good way to say this. That's just an awful. Okay, so in the case that j is greater than or equal to I, Pij of t, this is the probability of exactly j minus I arrivals in an interval, any interval of length t. And that's a Poisson number of arrivals. So we get e to the minus lambda t to the j minus I over j minus I factorial. And so let me summarize with a set of brackets here. This is going to be 0 if j is less than I, and it's going to be e to the minus lambda t to the j minus I over j minus I factorial if j is greater than or equal to I. And this is holding for any t greater than 0, but it will actually hold when t equals 0, as long as you define 0 to the 0 to be 1. Because if we want to move from some I to some j in 0 units of time, you can't move in 0 units of time. But if j is equal to I, then that's just fine. This is 1 if j is equal to I, and it's 0 if j does not equal to I. And this transition probability we have up here will actually hold as long as, so t is 0 and j equals I is going to be a 0 to 0. So as long as you define 0 to 0 to be 0 to the 0 power to be 1, then this will also hold when t equals 0. So nothing really new, just a new notation. And we wrote out a formula for it based on what we know about the Poisson process. Okay, so next, what I want to do next is to go into the idea of a stationary or limiting distribution for a continuous time Markov process on a discrete state space. But we're going to need some other processes first for this to make sense, because the Poisson process is non-decreasing. It's just going up. And as long as you have a positive arrival rate, and we always do, we always have the rate parameter lambda greater than 0 for a Poisson process, this is just going to wander off. The number of arrivals is going to keep increasing. So we know there's no stationary distribution, because a stationary distribution has to hold even for any fixed number of time points. And so at some time, if you have a distribution that looks like this, maybe it'll look like that again. Yeah, so eventually it's going to start going way up, right? Because it's just increasing. So because it's non-decreasing, so staying flat or increasing, there's no stationary distribution. And there's also no limit unless you want to say the number of arrivals is infinite with probability 1, but we never do that. We never describe random variables as infinite with probability 1. So no stationary distribution and no limiting distribution. And although that's what I want to talk about next, this is not a good example. So before defining stationarity and limiting distributions for a continuous time process, I want to generalize the Poisson process a little bit to make it more interesting. Okay, so the Poisson process with rate lambda. Let's look at our definition 3. I don't want to look at all of it, but in our definition 3, we have that the probability that the number of arrivals in some time t plus h minus some time t is 1. This does not depend on, because of independent increments, we never put this stuff here. N of t equals I. So if the number of arrivals by time t is I, what's the probability of one arrival in a next interval of time that's not overlapping? By independent increments, this is just the non-conditional probability. And this is lambda h plus something that is little o of h by definition 3 of the Poisson process. And now I want to stop ignoring this information. So if we think of arrivals in a Poisson process as births in a population, if we're looking at on the y-axis, a total population size and time, then the arrival rate lambda, it would be nice if we could make it depend on the total population size. So if you have individuals cell splitting or individuals giving birth, if you have a larger population, maybe the birth rate is going up just because there's more people there to give birth, or maybe it's going down because there's some kind of competition, like there always is in my isopod bins. Population, the rate of birth could possibly, or we might want it to depend on the current size. This is how we're going to define something known as a birth process. A stochastic process. We're going to start getting a little more general, and they're not going to be simple counting processes that always increase, although a birth process will. So I'm going to switch to more generic continuous time discrete state space notation and stop using the N of t unless it's a Poisson process. So this collection for all continuous t greater than 0 is a so-called birth process if it is a Markov process. So I'm not getting Markovness out of my definition here. This is actually part of the definition. We haven't done that before. On the state space S, consisting of all non-negative integers, again, you're thinking of it as a population size, such that we're going to use the little o of h stuff. So the probability that the number of people at time t plus h minus the number of people at time t is equal to 1. Conditioned on the population size at time t is equal to I. So current population size is I, and this is the probability of one birth in the interval from t to t plus h. And we're assuming h is small. This was lambda h plus little o of h for the Poisson process, but now it's going to be a lambda sub I, something that could depend on the current population size. And then the rest of the little o stuff looks the same. So the probability of greater than or equal to 2 arrivals, given there's currently I people in the population or things in the population, that's not going to be allowed to happen with very high probability. It's going to be super negligible. So little o of h. And the remaining probability here is equal to 0. And that should be 1 minus the sum of the other things, which is going to end up being 1 minus lambda I h plus little o of h. So this is how you define a birth process. And again, we had to put Markov process in the definition because this stuff alone is not going to give you something that is Markov. We did prove that the Poisson process is Markov using I, double I, and triple I of definition 1. But here we're actually saying it needs to be Markov and have these transition probabilities over short intervals. So a Poisson process is a really boring birth process, right? With constant lambda i's. And so I want to bring out some examples of where you might use a birth process in terms of, it doesn't have to be a population. So examples, but before that, I really need to essentially do your homework if you're paying attention. We really need some important computations that I was hoping you had already seen, but I need them today. So this might help you with your homework if you figure out what I mean. One important computation we're going to need is something like lambda h plus little o of h to the n. How to simplify this in terms of little o of h. And all of the simplifications I'm about to do are based on the binomial theorem, which says that a plus b to the n is the sum over all k from 0 to n of n choose k, a to the k, b to the n minus k. So I want to simplify what I have here and try to get some terms out. And so I am going to use that binomial theorem. I'm going to let this lambda h be A and little o of h be B. This is the sum from k equals 0 to n of n choose k, lambda h to the k, and then little o of h to the n minus k. Okay, so we know that little o of h times little o of h is again a little o of h function. We proved that. And so if you multiply by another little o of h function, it is again little o of h. And if you multiply by another, it's again little o of h. And if you multiply a little o of h function by a constant or h or a higher power of h, that's not going to destroy the little o of h-ness. If you take a little o of h function and divide by h, that may no longer be little o of h. But any multiplication by h or a constant is not going to change the fact that you have something that's little o of h, which means that every term in this sum is little o of h except for when the little o of h goes away. And that happens when n equals k. So we're going to get the n equals k term, which is n choose n, lambda h to the n, and then you get the little o of h to the 0, which is stuff to the 0, which is just 1, plus all of the other terms are going to be little o of h. Let's just look at one of them, like n choose 3, lambda h to the 3, little o of h, well, assuming n is not 3. Little o of h times h cubed is still little o of h. And multiplying by another constant out front with respect to h, it's still little o of h. And adding little o of h terms is still little o of h. So basically, this is the only surviving term and everything else little o'd out. And n choose n is 1. So this is lambda h to the n plus little o of h. So let me summarize that. This is an important computation we're going to need over and over again. This will be given to you on the next exam. This is lambda h to the n plus little o of h. And just because it's given to you on an exam doesn't mean I wouldn't ask you to prove it. But if you're using this in a computation like we're going to do today, you would be allowed to just grab it off that sheet. Computation 2 is just looking at 1 minus lambda h to the nth power. Why am I looking at these 3 particular computations? Because they're going to come up over and over again for us. So I want to use the binomial theorem again on this, and you could let this be A and negative lambda h be B, and you'll be fine. But I like to have this more complicated exponent be on the 1. Like if B is 1, I think it looks a lot nicer. So I'm going to let B be 1 and A be lambda h, and then this is A plus B again to the nth power. So by the, oh, this needs a color and a squiggly thing around it. So this is the sum as k goes from 0 to n of n choose k, negative lambda h to the k, 1 to the n minus k. So that's gone, and that's why I like to put the 1 over there. And then we know that if we have a polynomial piece here with an h squared or higher, that is little o of h. So the only terms to survive this are going to be when k equals 0, which is going to make the h's completely disappear, or when k is 1, which is going to leave us with just an h. So I get the k equals 0 term, and I get the k equals 1 term. And the rest all have h squared or h cubed or h to the 4th. The rest are all little o of h. And so simplifying these, n choose 0 is 1, negative lambda h to the 0 is 1. So this whole first term is 1. And then n choose 1 is n, and negative lambda h to the 1 is negative lambda h. So we get actually minus n lambda h plus little o of h. So there is our second common little o of h simplification for a birth and death process. I haven't defined that yet, but soon we're going to allow the population to decrease. This is another important one. And then the third is just a combination of these. So something like 1 minus lambda h plus little o of h to the n. So by our property 1, we had lambda h plus little o of h to the n, and we showed that that was lambda h to the n plus little o of h. And this indeed will be 1 minus lambda h to the n plus little o of h. And maybe that's not entirely by property 1, because this is not a constant times an h. So maybe it's not enough to say 1. So it's similar to 1. You can use the binomial theorem on this, but I don't have like an h minus lambda h, because then I could say I've got 1 minus lambda h, and I don't really have that. So I guess it's not exactly 1, but I claim, like 1, that you'll get this. So yeah, if this is one of the ones on your homework, show that part. And then definitely by 2, you get that this is 1 minus n lambda h plus little o of h. And you get this other little o of h going along for the ride, and those will combine to be a single little o of h function. So the third thing, 1 minus lambda h plus little o of h to the n is 1 minus n lambda h plus little o of h. You might want to keep those somewhere because you're going to use them a lot. So we define a birth process, and then I took this aside into these computations so that we can actually see some examples of birth processes. So for my first example, I want to talk about what is known as a linear birth process. It's also known as a Yule process after some statistician named George Yule. So here is the setup. We have a population in which no individual may die. And then for any small time interval, t to t plus h, each individual alone will give birth to another individual with a given probability. So each individual will independently, this is just the definition for a linear birth process, independently of all else give birth to another individual with a probability that is proportional to the length of the time interval, which is h, and it's going to be like that, something that looks very Poisson. So lambda h plus little o of h. And you only need one individual to give birth. It's not really like a mating process. So this is usually used in physics and bio applications where you have particle splitting or cell splitting. So 1 becomes 2. And then we're going to define x of t to be the population size at time t. And so I want to show that this is a birth process and give the birth rate. I never defined that, but the lambda I in the birth process is known as the birth rate. It's the rate of increase of size 1 in the population at the instant when the population size is I. So question, is this probably more like a statement, show that this is a birth process? Is this a birth process? And if so, what are the birth rates? Okay, so I guess there's things to show about it being Markov. That's actually not that hard to argue, but I don't want to focus on that. I want to focus on the little o calculations. So let's look at like the probability that we increase the population size by 1 at the moment the population size is I. So there's I individuals in the population. And in the next tiny interval of time, we're looking at some t to t plus h, where h is very small. How can we describe this probability given the setup here? What we have to do to get this to happen is we have I individuals, and each one will give birth to a single other individual in this time interval with this probability. So out of the I people, we have to choose one to give birth. And the birth probability is lambda h plus little o of h. And we get one of those. And then we get the remaining 1 minus lambda h plus little o of h. Notice I turned a negative into a positive. We've talked about that you wouldn't be wrong if you wrote negative little o of h, but it would just be a little bit weird, to the I minus 1. So I individuals, we want to see exactly an increase of exactly 1 of the population size in this tiny interval of time. And now I want to use the things we just showed. So I choose 1 is I. Lambda h plus little o of h to the 1 is just lambda h plus little o of h. This other thing is the third in the list of computations we did. This is 1 minus I minus 1 lambda h plus little o of h. So that is the third computation, although we had an n, not an I minus 1. So like, I don't know, computation 3. And then we need to multiply these things. There's an I, which is just a constant. And you can like multiply this out. You get lambda h times I, and that just has 1 h in it. So we get I lambda h, but like lambda h times this guy would have an h squared in it, and multiplied by I, it's still an h squared term, and that is little o of h. And if you multiply an h term times a little o of h expression, it's still little o of h. You could destroy the little o of h-ness if you divide by an h, but not multiplying by an h. And a little o of h times 1 is little o of h. A little o of h times an h term is little o of h. And a little o of h times a little o of h is little o of h. So all the rest of the terms are little o of h. And this has the form lambda I h plus little o of h, where we're defining the birth rate when the population size is currently I as I times the constant rate that we were given per individual. So number 1, we got it into the right form to show it's a birth process, and we have picked out the birth rate. And we wouldn't be finished checking until we checked 1 more probability statement out of the 3 that were given. So I am going to, I don't know, I'm going to do the n greater than or equal to 2, I guess, because I think that's the slightly harder one here. Actually, yeah, I think this is a good one to do for several reasons. So what is the probability that the increase in population size is 2 or more at the instant the population size is I? This is supposed to be little o of h. And so how can we get an increase of 2 or more? We can, out of I people, choose 2 to give birth. The birth probability in this interval of length t to the interval of length h is lambda h plus little o of h to the 2. Yeah, And then we get the rest of the probability, 1 minus lambda h plus little o of h. You know what? Let me not do this all at once. Let me change this, I'm so sorry, to an equals to. I don't know if that's worth it, but we get this to the I minus 2. And then here I get a little o of h term to start out with. And what this is representing is something I don't want to take the time to show. This says that multi-generational births are negligible. So if you have I people in the population, to increase by 2, you're going to need 2 out of those I chosen to give birth, and not one person to have a child and then a grandchild. We could actually write out what that would mean. We would have to condition on when that birth was in the interval from t to t plus h, and then look at the probability that there is that child had another child in the rest of the interval. We could do that. It's tedious, and it will be little o of h, I claim. So negligible is multiple generational stuff. Okay, and so from this, yeah, we get I factorial over 2 factorial. I get 1/2 I times I minus 1. That's what's left when you simplify that choose stuff. This computation we did today, that was the first computation in those computations we did. This is lambda h squared plus little o of h. This was the third computation. This is multiplied by 1 minus I minus 2 lambda h plus little o of h. And that was it. So we've got some constant stuff. And then we've got like this guy times this guy, and this guy times this guy, and this guy times this guy, and then this guy times this guy. And if you look at this first term, lambda h squared, so lambda squared h squared times 1, that's little o of h. And when you multiply it by this constant, still little o of h. And if you multiplied lambda squared h squared by little o of h, still little o of h. And everything that you get by multiplying these out have powers of h that are squared or higher or multiplied by little o of h. Everything is little o of h. So yeah, I'm using the fact that like, okay, 1/2 I minus 1 lambda h squared times say I minus 2 lambda h is just a big constant times lambda cubed h cubed, and this is little o of h. So that's just one of the terms in the multiplication, and they all turn out to be little o of h. But to show this is a birth process, this actually isn't one of the 3 things. We do want to show that this being greater than or equal to 2 is little o of h. And that would come from adding a bunch of terms. Or maybe not. Maybe I would go with the equals 0 part. We showed the equals 1. And maybe showing equals 0 would be the next easiest one. And then the greater than or equal to 2 term would just follow. But the reason I wanted to go through this with 2 people in the population is not because it helps us establish our birth and death process, because it's actually not one of the 3 conditions, but to talk about this multi-generational thing. So 2 births means 2 separate individuals gave birth in a tiny interval of time. Not multi-generational and not one person having 2 births in that interval of time. We have not finished. I have more calculations like this. I have not finished establishing that this is a birth process. We looked at the I equals 1 case and got this. And so I would look at the probability that xt plus h minus x of t equals 0 given x of t equals I. Actually, let's do this really, really quickly. There's no problem with multiple births or anything like that. Out of I people, we have to choose 0 to give birth. The birth probability for any individual is lambda h plus little o of h, and 0 of those happen. We get 1 minus lambda h plus little o of h for the rest of the population, the rest of the I minus 0 people. This is 1, this is 1. So we get 1 times 1, and this is one of our simplifications. It is 1 minus I lambda h plus little o of h. So this whole thing is 1 minus I lambda h plus little o of h. And fortunately, that matches 1 minus lambda I h plus little o of h because we have already defined our lambda I to be I lambda. So the birth rate when there's I in the population is I times lambda. We're going to show soon, maybe the end of today, I don't know if we'll get to it, or the beginning of next time, that for any continuous time Markov process on a discrete state space, the time you spend in a state, it's called a holding time. When you hit some state I, the amount of time until you leave that state is necessarily exponential. And what you're seeing with this I lambda is actually I people racing to have an offspring. I exponentials with rate lambda all racing, so that individually they have rate lambda, but as a whole, the next birth is the minimum of those I individuals giving birth. Cool. The next example of a birth process, by the way, this isn't helping us get a stationary distribution because these are also non-decreasing processes. So it's not until we bring death into the equation that we can get something going up and going down that could potentially have a stationary distribution if the rate parameters cooperate. But I have one more example of a linear birth process, and that is, of a birth process. And that is a linear birth process with immigration. So the setup is we have a linear birth process, what we just talked about. And additionally, individuals can come into the population with some constant rate. By the way, the birth process, starting with the lambda, which gives us the lambda I is I lambda. So the same exact setup before. And additionally, people are going to migrate in at a constant rate nu. I'm going to use a nu. What that means, that doesn't really tell you anything, but when you see that in the context of a stochastic process, things entering your population at a constant rate, this means that immigration is a Poisson process with rate nu. So how did I know that? It's just kind of the definition of what people mean in stochastic processes when they say people are coming in at a constant rate. So it comes with all the great stuff of a Poisson process, the assumptions that the number of immigrants in non-overlapping periods of time are independent, stuff like that. So is this a birth process? I would hope so. Otherwise, it's a terrible example. And what are the birth and death rates? There's no death, sorry. So I want to look at 2 out of 3 of these conditions. Let's look at increasing the population size by 1 when the population size is currently I. So this can happen in 2 ways. This is the probability of 1 birth and 0 immigration given the population size is I, plus the probability of 0 births and 1 immigration. given the population size is I. Because I'm not talking about multiple things here, I don't need the little o of h to deal with ruling out multi-generational stuff. But you wouldn't be wrong if you wrote that, because 0 is a little o of h function. So if you want to tack on a plus little o of h to all of these, you're not going to go wrong, because even if there's nothing there, 0 is little o of h considered. So what we have is, and I needed to add more to this definition. So they're migrating in at a constant rate independently of independently of the birth process. Now we can have them migrate in dependent on the birth process, and that will be another example, but independently of the birth process, just to start. And that means that when we're doing these commas, these ands, we get to multiply probabilities. So this is the probability given xt equals I times the probability given xt equals I plus the probability given xt equals I times the probability given xt equals I. So that's me not writing one birth, 0 immigration, all that stuff. So one birth, there's currently I in the population, so we have to choose one person to give birth. Each person will give birth with some probability lambda h plus little o of h in some small time interval of length h. So we get that to the first power. So that's the success, like giving birth is success and not giving birth is failure in this example. 1 minus lambda h plus little o of h to the I minus 1 multiplied. Let me make this like big and yellow. So the probability of 0 immigration in a tiny time interval of length t to t plus h. The immigration process is a Poisson process with some rate nu. And so this is a Poisson number of arrivals in an interval of length h. So this is going to be e to the minus lambda h to the 0 over 0 factorial. This should be, these parameters should be nu. New. Yeah, and so the other case, 0 births, out of the I people, we have to choose 0 to give birth. The success probability, we get 0 successes, so we get that to the 0 power. We get the rest of the probability to the I minus 0 power, and then I'm going to multiply that by the probability of one birth in an interval of length h, according to a Poisson process with rate nu. That's e to the minus nu h to the 1 over 1 factorial. Okay, so the first term is I choose 1 is I, then I get lambda h plus little o of h. Then I get, simplifying this with a third computational simplification. I get some square brackets here because I could barely read that. We get 1 minus I minus 1 lambda h plus little o of h. And then we're going to multiply by, so of course, nu h to the 0 is 1, and 0 factorial is 1. And e to the nu h with a Taylor series expansion is 1 minus nu h plus little o of h. If you missed the last class, this has got to be terribly scary. Don't freak out. We're going to be doing this for a while. You will catch on. You're going to be fine. But yeah, I got that. So I still need my next line, but that e to the negative nu h is 1 minus nu h plus nu squared h squared over 2 factorial minus nu cubed h cubed over 3 factorial plus, and these are all little o of h terms. So we get just this part plus a little o of h part. Okay, so the next line, which is at the top of the screen now, I choose 0 is 1. This to the 0 is 1. This to the I by computational simplification 3 is 1 minus I lambda h plus little o of h. And then over here, I've got nu times h, 1 minus nu h plus little o of h. So that part comes from the E. Whew, lots of stuff here. But if you multiply this out on top, like I get this I and the lambda h and the 1 and the 1, that is I lambda h. I lambda h and the negative I minus 1 lambda h is going to be an h squared term, which gets put into the little o of h stuff. As another example, a little o of h function times nu times h is still little o of h. And I claim if you go through all of these, they're all little o of h up there. I'm going to keep the second line as the second line. Okay, so I have this nu times h times the 1 times the 1. And so that term is going to survive. And then as an example, this 1 times this term, which also gets multiplied by this term, has an h squared in it and is little o of h. And in fact, everything else is little o of h. So putting these together, I get I lambda h plus nu h little o of h, and then putting them into that birth and death process form, I get I lambda plus nu h plus little o of h. And this is like a lambda I h when we define the birth process, where lambda I is defined to be I lambda plus nu. So that's the birth rate for this process. And once we show that the times you spend in each state are necessarily exponential, then this rate makes a lot of sense because we have I individuals all racing to give birth. Each will give birth after an exponential amount of time with rate lambda. So the first birth will happen after an exponential amount of time with rate I lambda, because that's what you get when you take the minimum of I exponentials with rate lambda. But we also have this another exponential time coming from the outside Poisson process. And if that happens first, then the next arrival will be the immigration. And so this is actually like I plus 1 exponentials all racing to happen. And so you can add up all those rates, and that represents the next event, which is the minimum of a bunch of exponential things, which I keep saying, but I haven't shown yet that there's any exponentials in here. To finish this off, we need to pick another one of the three conditions for a birth process. I think the 0 condition is easier than dealing with all changes greater than or equal to 2. So t plus h minus x of t equals 0, given x of t equals I. This is just one thing can happen here. This is no birth or 0 birth and no immigration. When we put death into the mix, then we have more things to consider because you could have a change of size 0 by having no birth and no death, or maybe 1 birth and 1 death, but not like multiple births and multiple deaths. That's all going to be little o stuff. So no birth. These are independent processes. And so the birth process, out of I get to choose 0 to give birth. The birth probability in a tiny interval of length h is lambda h plus little o of h. We get that to the 0. The rest of the probability sits over here, and we get that to the I minus 0. And that gets multiplied by the probability of 0 immigrants. And the immigration is a Poisson process with rate lambda, and the length of the interval is h. So this is e to the minus nu h to the 0 over 0 factorial. The I choose 0 is 1. this to the 0 power is 1. I'm going to simplify this next guy with the computation number 3 that we did. This is 1 minus I lambda h plus little o of h. And that gets multiplied by just the e, which is equivalent to 1 minus nu h plus little o of h. Yeah, again, if you miss this little o stuff or you're not good on it yet, this has got to seem terribly frightening. It's not bad. You will get it, and let's talk. Okay, 1 times 1 is 1, and then I get 1 times the negative nu h, and I get 1 times the negative I lambda h, and everything else is little o of h. Like 1 times little o of h is little o of h. The I lambda h times little o of h is still little o of h. So checking them all, we end up with this. And so these will combine in the right way that verifies that we were right with our lambda I, because we defined lambda I already to be I lambda plus nu. So we got into the right form, which is enough to show it's a birth process. That took a lot of time because that's tedious stuff. The next thing we're going to do is a very exciting theorem, and that says for any continuous time Markov chain on a discrete state space, it doesn't have to be Poisson, it doesn't have to be a birth process, it doesn't have to involve death, which we still have to define, but any continuous time Markov chain on a discrete state space, the so-called holding times, which are the times you spend holding in a state before you change, we're going to prove that they're necessarily exponential, and we're going to get that from the Markov property next time on Markov processes.